No, no, I'm not saying that. I am saying that when it reflects off the board and reaches the camera on the other side, it's
So how
still
did it
going to
get there?
widen just like it did when you did
No,
the
no, no,
first
no.
experiment.
No, no. When I shine the laser, you've ever played with your cat with a laser? It stays a little point as you run around your room. It's a red little point. Well, we thought going 4 miles across that we would be able to see that point remain the same. But over a 4 mile stretch, that point became 8 to 10 feet wide. So we knew we couldn't go that distance with the laser itself. But then, as we're standing back and forth between this huge body, it hit me that we were able to, with the camera, zoom in and see that that's what was happening on the other side. So I said, wait a second, we just need to go to the other side, shine that laser over there at the water level, and see if the camera can see it, because it needs to be 10 feet behind the curvature, 10 feet underneath it, which means
Well,
there's no way the camera can see the laser beam on the other side of the water unless
it
it's
would be
above.
obstructed.
Right, it'd be obstructed
Well,
by
in
water.
order to make this work, you guys are going to have a laser beam go 40 miles, not 4 miles. You're
Well,
not
Okay.
going to you're
and we
not
know
going to
that.
convince anybody with 4 miles.
Well,
All right then.
it wasn't a matter of proving the world is a lie. It was a matter of, these are the kind of things when we say we didn't pop out of a cave and say the Earth is flat. It's been a process that people have gone through, and where we meet resistance is usually things like some of the things that you've said that are just, nope, what NASA says is correct about that, but not about this other thing. And you got to take it with a grain of salt, but not that. Those pictures are real. And so what we're trying to say is, we wanted to go out and do these little experiments. If we would have went out and it would have showed a curvature at 4 miles, I'd be doing something else today. I wouldn't be here putting my name out there as a flat earther unless I honestly spend every day realizing more and more
Right.
that it's flat.
And let me throw this in there also, Jaron. Robert, my background in electrical engineering, one of the things that I used to do was I worked with terrestrial microwave. Now, at the time, I never thought about this at the time, but we never ever made calculations to allow for the curvature of the Earth. And many of our microwave sites, which propagate virtually identically to the way that light propagates, were 60 miles apart. And when you calculate the curvature of 60 miles, it doesn't really quite add up, because the towers that these things sat on where typically the antennas were mounted at no higher than 50 foot above the ground. Now, granted, microwaves are typically put on the highest points in the plant, that we can do, but this isn't always possible, especially when we were building the sites across Kansas. Kansas doesn't have that many high places. Nevertheless, we were still pulling off those 60-mile shots. Now, you could argue that there is, well, like the newsman, you could argue that there's some sort of mirage effect at work here, but the communications are entirely too reliable, and again, we never had to calculate for any curvature of the Earth. So when we're talking about something like that behaves just like light, again, the curvature of the Earth should have absolutely blocked those microwave signals, because they do not propagate through solid objects when you're dealing with anywhere from 6 gigs to 12 gigahertz, which is what we were shooting these beams at.
And Robert, let me just say these couple things, and hopefully you take them with you and look into this, because it's something that it's not as simple as, oh, we have 2 or 3 facts. Look into surveying. When they do any survey job, they don't take in the curvature at all. Nothing. Look at bridges. Every bridge that's ever been built, they've never taken curvature into play, and when they do, it is the one that's the Lake Pontchartrain bridge that's 24 miles across. They say they had to make the bridge 3 inches longer to account for the curvature. The curvature, when you do the math, 360 feet. That's taller than the Statue of Liberty. And yet, that's what we have to do to make up for the curvature, is a 3-inch change.
And that's over water.
Yeah, what about lakes? There's tons of lakes, so you can see the other side of the lake at 20, 25 miles. The curvature, again, should be 600 feet below, but water's flat. Look at Michigan to Chicago.
Wait a minute. Wait 1 second. Okay? The whole premise here that you're working on is that water's flat.
Yes, it is.
No, you can't do that.
How come?
You can't do that. Because if you have a spherical Earth, then water is not flat. It curves with the landmass.
But we can't measure it.
Yeah, but we can see no curvature. So
We'll
how,
measure it.
how
You're
yeah.
not going to see a curvature in 4 miles.
No,
What about 60?
Well, that's with microwaves that bounce off everything
It's
that
also
we
with
have.
visual. Look at the weatherman. Who was the weatherman that was
Wait,
shooting
wait, wait, wait.
across
You asked me
Chicago?
about microwaves. I'm telling you,
All right.
microwaves bounce off of a lot of things, and they can make it from one antenna to the next without going straight from one antenna to the next.
Oh, now
that's where
you're.
they aim them.
I'm sorry, Robert. You're in my area of expertise now, and I'm telling you that is not the way they work. They're not. We're not bouncing it off of things. We are shooting straight from antenna to antenna.
Yeah, I know, but you're still going to get a bouncing effect. That's why the waves go
Off
much
of
faster
what?
when the sun is out than when it's not out, because
Well, we
the
believe
sun is
that too.
affecting the atmosphere.
Well, we believe that the sun is affecting the waves. It goes around the equator. Of course, it's going to pull the
So what are you
water
saying
with
they're
it.
bouncing off of, Robert? What are they? Are you saying they're bouncing off the ionosphere?
Yeah,
Well, they're
they're
not
doing
aimed
not
at the
aimed at that.
ionosphere.
bouncing off the atmosphere. Yes.
Well, then what is the point of aligning the antennas, which have extremely narrow beam widths, and pointing them directly at each other over a flat surface?
Because some of them are going to go directly toward that position, and they're going to bounce off anything that's hit the antenna on the other side.
Yeah, the only problem with that is when they arrive at the other side, if they're going at two different distances, you're going to have a massive phase distortion in the two signals. And I'm sorry, but that does not work, especially when you're multiplexing 10,000 channels on an analog signal. That does not fly.
Well,
And
in
that
that
actually
case, that's why they use satellites, but you guys don't believe in the satellite.
No.
Yeah, but if they use
and
satellites, and they would be pointed at satellites. They're pointed at their. And I've had, again, I can't prove this any more than show you the emails. I've had 3 or 4 people who work with the Army in satellites email me and say, you know what, you're right. We absolutely aim satellites 50 miles point to point, and you have to measure it with basically the Mercator projection, the flat Earth map, not the round one, but the actual layout. You can measure it out just like they do with ham radio, and aim it there, and it hits the other satellite at 50 miles away. The curvature should be 1,800 feet. I mean,
Right.
it's just ridiculous. How is it going down that
Let
distance?
me tell you something else about that, Robert. If you look up over the horizon radar. Okay, now when I was in the Air Force, that's what I did. I worked in radar. Okay, so in over the horizon radar, the theory of it is that they bounce the radar or the microwave signal off of the ionosphere. Okay, typically the F layer, and then that's how they say they get that distance. And there is also a natural refraction of that radar signal that will draw it down to the Earth. Now that's all fine and good for the outgoing signal, but you have to remember, once it bounces off of whatever they're bouncing it off of supposedly, and it hits its target, then it also has to take a return path at that direction, and that simply is not possible. And that's something that people never take into consideration.
Why isn't it possible? Why isn't it possible?
Well, first of all, because you have the natural refraction of it, and then you're talking about that it would have to bounce back up and come back from that same exact trajectory.
Well,
And
the microwaves go out in radial directions, just like a light beam does.
Yes, but the way that radars track distance and speed of an object is it's referenced off of a coherent oscillator that is phase compared from the time that it is transmitted out to the time that it comes back, and using simple Doppler effect math, it is calculated. That's how an object's speed and distance is calculated. If it is taking multiple paths, you're going to have multiple phases of signal coming back. And again, that would completely invalidate any premise of how the radar works.
Well, no. What they do is they just filter out the bad phases, and they take the one that's more distinct, and that's the one they go with.
Okay, so if it's bouncing off something that's closer, then you're saying that it's going to take the dominant signal strength every single time?
Yeah.
Well, okay, that would be great, except that isn't how the signals are processed in the radar. It's a single pulse out and a single pulse back. We are not dealing with multiple phase, multiple pulses coming back at different phases. That is not the way radar works.
Yeah, well, the mechanism, have you built the mechanism inside that interprets the signal, or do you just
Yes.
know how? You've built the
I have,
mechanism?
no, I have not built it specifically.
Oh,
No,
okay. So then you don't know what computer program they're using in order to differentiate those signals, do you?
Yes, I do. I do. In fact, I understand very clearly the circuitry and how it's differentiated. That's part of the training and understanding the radar engineering. And I'm telling you that it does not compare multiple signals. It does not differentiate any stronger signals that come back. It is looking at a single signal that is reflected back. And again, it is always from one path, not multiple. And
yeah.
So that's what I'm saying.
So okay, well, what I would say is this. I'm going to do some more investigation on this radar microwave issue.
Okay.
But I do know this, that within the margin of error, I can see it working, and then they're going to reach a point where it's not going to work, and that's why they have to go to satellites. Anything over 50 miles or so, it seems to be the case that they're going to have to go to satellites. Unfortunately, since you don't believe in the satellites, then you have this big problem, is how you're going to measure distances over 50 miles.
Well, it's all right. Then let's look at that for a minute. Yes, you're right. I don't believe in satellites, not anymore. And as somebody that used to work in that industry, it was a little bit difficult of a hurdle for me to get through. But what I'm saying is if satellite technology was all that prevalent, then why, first of all, are we laying all this fiber optic cable? Why is it that the Weather Service launches thousands of weather balloons every day to take observations and generate a weather pattern for for anywhere in the world, for that matter? Why do they even waste the time if they have tens of thousands of satellites up there that are capable of simply snapping that picture? Again,
Robert, look up Google
preponderance of evidence.
Look up Google.
Because it's a matter of money, and it's a matter of logistics, and it's a matter of the fact that sending a balloon up is not expensive at all.
They do it every day.
Cover a local region. That doesn't prove anything because they use weather balloons.
Okay, how about Google? Google Lunar is taking.
They're not cheap.
They're not cheap, and like I said, Robert,
it's twice a day, Bob.
Look at the work you have to do to have somebody go out there. You have to pay the person to go launch the balloon. I mean, if you're talking about building a satellite, it goes up there. They say there's satellites up there that have been in orbit for 40 years. Like, it just has a little battery pack. It shoots out a little gust of air every time it needs to readjust itself. It's ludicrous. I mean, and these are the things where we're saying if they
Wait a
just
minute,
had...
what's ludicrous?
So these satellites have to stay in their orbits, correct?
Yeah.
But there's tons of radiation that is coming from the sun that would adjust the where its trajectory is, and it needs to be immediately corrected, or else everyone's going to lose their DirecTV.
Well, yeah, those satellites are corrected. Their orbits are corrected.
How?
Yes.
How are they corrected? Is what I'm saying. They're corrected with a little burst of air. It's like a little squirt gun.
Which violates Newton's third law.
And it's all...
No, it doesn't violate Newton's third law. If the orbit is deteriorating and they give it a thrust to put it back in its orbit, that's obeying Newton's laws.
What is it thrust against, Robert? How can it thrust against a vacuum? What is it thrusting against when it's in space if it's in a vacuum? What is there to work against? If you're going to say that, if you're going to use the example that NASA uses, that this is how they say their rockets work. They say take a medicine ball, sit in a chair with wheels on it. Lift your legs up and push that medicine ball away from you, and the medicine ball will go one direction, you will go the opposite direction on your wheels. That is how they say their rockets work, because they're also trying to claim that their rockets are not working against any external force as Newton's third law would require. What they are describing there is the force called recoil. And the problem with a recoil force is that in order to be able to continuously recoil off of something, you have to be able to have at least an equal amount of mass to offset against.
Right, a firm stance.
And you would have to carry that mass with you. And since
if there's something strange in your neighborhood, who you gonna call? If there's something